Yeah, so first I would like to thank Professor Guo for the introduction. And second, I would like to thank the Soft Science, especially the editor-in-chief, Professor Ren, for the invitation, and also Professor Sun Jiangyu's invitation. It's really my honor. So since I know this is the first speaker of this Candle in Wine seminar, so it's really my honor. So as part of the editorial board member of these journals, I would like also to say something about it. So I think this journal is really a nice journal. It's focused on these flexible and soft materials. It's even broader than this. It's the soft science. So before I start my presentation, I hope we can pay more attention to this journal. So I believe we can do this very good job. So on this journal, okay. As Professor Guo introduced, I'm Xingge Yu, so from City University of Hong Kong. And today I would like to share our recent works on the skin electronics. So we mainly focus on the intelligent healthcare monitoring and also the habitat feedback. So we sometimes also call it the touch VR. So which can be applied in like a virtual reality or recent very hot topic called Metaverse. Okay. So I think first thing we need to briefly talk about what is the Metaverse, since everybody is talking about the Metaverse. So in Chinese, 元宇宙 is a really hot topic since last year. So I think the Metaverse is something has to be because the pandemic last for 2.5 years and so change our life a lot. So even now you see, so we do this kind of seminar online. So I also saw a lot of friends I haven't saw a long time ago. But typically, so this should happen is offline, okay, in person. Well, so just under this situation, the Facebook suggest one idea topic, which was Metaverse in 2021, last year. And so they hope in the future, in the near future, so we can build another type of universe that is in parallel of our physical life. So we call it a Metaverse. In the Metaverse, we definitely will have one character or user that represent ourselves. So in that universe, and we can do even the same things in the real world. For example, is the online meetings such as this. Okay, so the difference compared to Zoom or Tencent meetings, so we are doing now is in the Metaverse. You can see as we represent in this slides. So people can feel more immersive feeling, just like yourself in the meeting room. And it can be also used in many other areas, such as the social media. You can think about it in the future. We can do like some kind of virtual traveling and also entertainment, playing game, and so many other things. That's just in another word, it's really huge. So the motivation of doing this, or why people think about doing this, also we can think about what we can do. So for this area, so this you can see from this slide, it's all the pursuit of the simulation. So we know, so the human body, so we have 5 major sensations. Okay, 5 major sensations. Well, the pursuing of the visual stimulation motivated us develop a very nice technologies such as the TV and cinema, silver screen. Okay, and the pursuing of the auditory stimulation, then we developed the acoustic devices, the headphones, as well as these nice speakers. So however, my question is, how about tactile? So we know touch feeling is one of the most important sensations. So among the 5 sensations, since we feel the world, first by touching. So let me give you like one short movie, which is the called Ready Player One. So in this world, to give you some idea of the Metaverse and also the importance of the touch feeling. Well, so in this movie, they are Metaverse. So they describe in the future world, everybody in the Metaverse control one gaming character, which represented himself or herself. And in this world, they can do a lot of things, just like in the real world. And especially pay attention here. See, 2 users can use their virtual characters, interact with each other, and they can feel the touch. Okay, they can feel the touch. So however, you see, so the touch is not really someone touch him, it's a virtually touch, but he can physically feel that by these suits, okay? So then we go back to the pursuing of the visual and auditory stimulation. So we know that we can see, we can hear. So however, how we feel tactile feeling. So we definitely need very nice instruments or devices. So, but the point is the current technologies on the tactile or haptic feedbacks, you can see that based on these very bulky and also down mode and the low resolution feedback instruments, and it still has a long way to go when you compare to the like a VR glasses or the headphones. So here I give you the example why we say that, we think that. So still use the Ready Player One, for example. In the real situation, so you wear such a suit and you can feel the virtual touch like shown in the bottom. So if we want to realize such like a technology or platform, so there's several things we need to meet the requirement. So first thing is must be thin, soft, and wearable. Okay, so and this is a significance of the soft science. Okay, and why we need soft. And the other thing is we need this such haptic feedback need to be multiple modes. So we don't want to only feel like a force. We want to feel temperature, or we want to feel fine texture, and we want to feel all the like a tactile information that in the physical worlds. Okay. And a lot of companies and the industries also try a lot of methods to realize such technology. So for example, so the Meta, so Facebook, so already so published such like a glove. So they use a lot of air bubbles, okay, and they use this air pump to pump and de-pump all these air bubbles, and then can provide you some like a force feeling, and you can feel the force and virtually when you grab something. So however, so I don't need to talk about the disadvantage of this technology. You can feel that. First, the thing is very bulky, it's irritating. Another thing is if we use such technology, so there may be some time delay because we know the pump and de-pump takes some time. And the most important thing is that you need very complicated connections, and you need to use this one in a very specific environment. So there's quite a long distance to go if you want to implement this one into the Ready Player One. Okay, so our job is to so develop something new than this one, and also really so make the Ready Player One scenarios is to come true. So that's the first work we would like to talk about. So in 2019, so we for the first time so report this wearable skin integrated haptic feedbacks. We know a lot of people working on flexible electronics, or most of the people working on flexible electronics focus on the sensing, okay, such as the physiological signal sensing, like the temperatures, heart rate, and so these type of things. So however, what we are different is we use electricity to input into this patch, and this patch can provide these force feedback, and you can feel that. And this is also called actuator, okay. And you can just think about it. This is one piece of the suit from the Ready Player One, so users so close, and it is included tens of these haptic actuators, and each one can be controlled on and off individually. So which is based on the electromagnetic driven force. So it's very simple, including one copper coil and permanent magnet, and you have a handle to hold magnet. When you input an AC electrical signal to the coil, it can generate AC, so alternative magnetic fields, and the permanent magnet will be vibrated there, and you feel the force. Okay, and the device is very small. And when you peel off the encapsulation layer, you can see that we incorporate a lot of so serpentine design of the circuits and the interconnections. And the whole device is stretchable and with this structural flexible design. And we also use the cheap mount size, so electronics, which can be soldered on top of the device, okay? And the whole device can be wirelessly powered by RF power and wireless communicated control, okay? So before we design this system, so there's several things we need to think about. So what type of the working frequency we need. So the most straightforward way is to go back to see the features of our skin. So we know our skin are sensitive to different types of vibration frequencies. So especially when you hold your cell phone, when your cell phone is vibrating, you can feel that very obvious. So the reason is, so the cell phone typically working at 200 hertz when it's vibrating, and you can feel that we are very sensitive to this frequency. Okay, and so the first generation of technology, so it's very easy. It's just that we comes out whether we can develop some like actuators working at 200 hertz can provide us so strong feedback. And there are actually some people is already working on the similar area, but on different directions, such as the Professor David Eagleman from Stanford University. So they use a lot of DC motor and just the seal inside of voice. And with the voice recognition system, when everybody talk about something, and so it can translate the signal into the electricity, and then so actuated these DC motors, and it can feel that, which can aid this hearing or visual impaired person to feel the external information rather than use their eyes or ears, but just to use their skin. Okay. Well, so our devices are definitely so quite different, because you see there are thousands of these small electronic components. However, so we use a lot of type of flexible electronics integration strategy and precising rules, and make all the devices very thin. After integration, its thickness is less than 3 millimeters, very thin. And with this design, we can like twist, stretch, and bend the device, which can still maintain very good performance. And it can also just directly mount our skin, so along the bone curvatures, so without irritation, and also it's a very conformal coated on skin. So this is how we make the actuator working at 200 hertz with a very high efficiency. So we know there's one concept called resonance. So one example is there was a group of soldiers trying to cross the river, and when they just step on the bridge, and the general also command all the people to go together, and then the bridge crashed, and because they go together, and then it's just meet the resonant frequency of the bridge. Well, so most of the time in the architecture construction, so we don't want resonance. However, in electrical design, so especially these MIMES design, we typically use this idea. Here, we use the resonant frequency at 200 hertz. And when it's at 200 hertz, you can use very small amount of power to get a very high vibration amplitude. And first thing is to save frequency. And second thing is you can increase the working efficiency. And this is a high-speed camera captured video, and you can see very tiny movement. So let me see as I can play. So, okay. So you can see that it's the high-speed camera so captured. So so this was used less than 2 milliwatt input. It can generate some kind of 30 to 40 micrometer travel amplitude, and which is good enough for our skin to feel that. Well, another thing we focus is the fidelity. So say if we have some Haptic interface, so we want one device, so one point provides you feedback. So if the fidelity is not high enough, what you can feel is the whole area can provide you some feedback. And after changing the arrangement of the neighboring actuators, we can just diminish these mechanical interferences, and the device can working very locally, provides you very high fidelity feedback. Okay. So with such structure, we also working on the electrical design and make all the devices working wireless, and with all the chips to control all the devices on and off. And here, so all the devices are working wirelessly and battery free, since we use the earth power. Okay. Another advantage of the device is we program all the chips together with one command. So then, when you switch on and off from one device to the other one, So there's almost no time delay, and you can see that when you switch one from the other. So the time delay is in several milliseconds. We cannot feel that at all. Okay. And here's the video show how it works. And this is our device, and this is the GUI interface we developed. And when you type on the tap screen, and the corresponding points will provide you feedbacks. So on the physical device, okay, and then you make it so works. So however, so we are talking about is working. So people cannot see because of vibrating. So 1 second, 200 times vibrate. And so we definitely cannot see that, use our physical eyes. So, but what we can do is we can use some laser points to leverage vibration. Think about it, when the laser point reflect the vibration on a projector, okay, projection on a wall, and so the vibration will be amplified, and you can see the vibration. And this is another GUI interface we developed. And on the left side is the GUI interface, and you can type so these individual points, and on the right is the laser point corresponding to these points. And you can see the vibration. It's not only working individual points, it can also working to work together to form a pattern, such as we write a letter N, and you can see that. And we don't need to reprogram it, just write another, just a switch letter U. And we also write on the City University of Hong Kong, the in short, CityU, and you can see that it's very obvious. Okay, so you can see the difference. So we can use such device working in many areas, such as the gaming. It's very easy to understand. So for instance, this gamer is aware such as suits and control one game character is fighting with the enemy. And no matter if fight, so the enemy or be punched by the enemy. So the particular, specific regions, will provide him, the habitat feedback. It's very immersive feeling for gaming. So another application area is the social media. So especially during the pandemic. So I believe a lot of people like me, so I have a long time didn't go back to hometown. And so especially, the grandpa and grandma may miss their grandson or granddaughter. And here, so we can just use our habitat interface to interact with the two group family members, and they can feel virtual touch by our device. So just a touching screen and can do this. Okay. So another application area is the prosthetic sensing and control. And this is our volunteer, and this is the robotic arm. So we know that we use the robotic arm can grab something. However, so no matter what type of thing he grabs, he cannot feel that because this is a robotic arm. What we can do is we can put the Haptic interface we call Touch VR, okay, at the end of his arms. And when he grabs something, the sensor will translate the signal and through the feedback signal and provide the feedback, and you can feel that. And here's the video. So with the assistance of such a Haptic interface, and he can easily control the force, and because he can feel the force when he grabs something. And definitely you need to integrate the sensors on top of these robotic hands. Okay. And here, it's we call it the second generation of our Haptic interface. The previous one is, I think, is good enough. However, so the density is not that high. And another thing is not very thin. Okay. And here, we use the hydrogel and the flexible electronics, integrate them together and to make all the devices working in a very miniaturized size, and all the control signals is and the circuits is integrated in such a small parts, and then can interact with the AR game. You see, you use the camera, and the AR game can capture a small animal is jumping on your hands. You can feel the tickling feeling. Okay, and another thing is our self-developed app can collect all these signals to provide a large amount of data to these AI guys. So they need this one. And now this work is actually under revision. So very positive comments from a nice journal and working on. So hopefully it will be published in next couple of months. Okay. So you can see that actually we would like to call our VR device is a human machine interface. Okay. no matter it's our Haptic interface is interact with prosthetic prosthesis or other things, is the human and machine interaction. And a human machine interaction, what we need is a closed loop. We not only need sensors, we also need actuators, because sensors control motion. And when you feel something, and you need actuator tell you this information. And then we suggest another idea, we call it a robotic VR, enabled by soft science. Okay, again, it's by flexible electronics. So here, so we suggest this idea. So we use the VR glass to like coordinate and interact with the robotics electronic eyes, and what the robots see and can project into a VR glass. And we can see we integrate a lot of sensors on the joints and the body, which can collect the activity, motion, information from the user. And then, so the robots can be perfectly controlled by the user. Well, so the sensor integrated on the robot's hands, so can collect the information. Well, so this information will be activated by the actuators, so on the bodies, on the user. So you can control the robots very accurately, because you can not only see, but you can also feel, okay? Just like a Venta, okay? So such devices, a system include 3 parts, is sensor and actuator and the control panel, okay? So which is integrated in the like a very thin format. It's also skin electronics format, okay? And can interact with the robots. Well, the sensor is a very thin, soft, and conformal coated on the bending parts of the joints, which can provide you very clear signal when you bend. And it's a sensor. So we use some like a simple design mixed in the neutral plane, and so can working very stably after 1,000 times of the bending. So another thing I want to emphasize is people may argue that if you use visual feedback is good enough. So however, let me give you one example. When you see something and do your decision, this really may take some seconds, okay? But if somebody types your back, so you may just turn back immediately. And this is tactile information. That's the nature behavior of human body. So that reacts to the tactile feedback so immediately. That's why we would like to incorporate the haptic feedback in such a robotic VR system. And here is an example. We can not only wirelessly control the robotic arm, so by different motions. Another thing is that when the robotic arm grabs something, and the sensors on the robotic arm can provide feedbacks to the actuator on the hand. So here, so when the robotic hand grab a balloon, so we can feel the force, and we can easily control that, okay? Use the proper force, okay? So with such system, we can use it in a lot of areas, such as the robot's manipulation. So that's replace the current exoskeleton design. So such as shown here is a similar thing that we mentioned here. And the good point is that when you use a different force to grab the balloon, and you can feel the different feedback and can control your force very precisely, okay? Another area we think it should be useful is for the COVID sample collection. And this is the COVID sample collection robots currently. So which is based on the visual feedback, and the medical staff can use a joystick to control that. So however, it's quite different from the conventional face-to-face collection. And you can think about it. So how about, so the medical staff use a VR glass and just doing the sample collection like what he or she are doing. So in the real situation, it can improve the efficiency a lot. So we believe that, okay. So another application area, so we think about it in the future, the green, age green is a significant issue. So we know that maybe 20, 30 years later, the major population is over 70 years old. So it will need a lot of nursing robots. Well, so how to interact with a human is very important, and we show the possibility by using our skin electronics-based robotic VR system. And we use the VR glass and to control the robots. So the robots can do, these are nursing jobs. So that's give you not only virtual feedback, but visual feedback, but also haptic feedback. So that's the first part I would like to talk about. So the second part, the second part is the flexible electronics working on the biomedical areas. So here is the motivation. We know the current healthcare system has the following drawbacks, such as the centralized. And another thing is a slow procedure, especially for testing, and it's very invasive. And the fourth thing is very important is expertise, highly rely on doctors' expertise. Okay, all of these will cause the current healthcare system expensive, time-consuming, and also may cause the misdiagnosis happen. Okay, so we think when we focus on these three areas, early detection and accurate diagnosis and on-patient monitoring can solve this problem. And the solution is very clear. That is soft electronics. Okay, and with novel materials and device design and bio-integrated electronics. And here is examples. I think a lot of people is experts in this area. I don't need to spend a lot of time to explain the significance of this area. And you can compare the difference between the traditional technology and the frontier soft electronics is quite different. Okay. Well, so one of the challenges, the mechanical mismatch between these current medical instruments and our bio tissues. So how to solve this mechanical mismatch will be very significant to the development of the device and materials. So when we combine the bio tissue and the device together, the interface must be materials, devices, and the system all need to be flexible. And we need such materials, devices, and system to be flexible, high performance, and to be biocompatible. So to meet these three situations, let me give you one example. So our representative work, we use the flexible electronics technologies to solve very critical problems. So the biomedical issues. Okay, that is for the tumor sensing and targeting. Okay, so before we talk about the details, so let's spend a very short time to talk about the motivation. So this is a procedure for the diagnosis of the tumor. Okay, so when physicians find there's the abnormal situation from the CT or MRI imaging technology, such as the contrast difference, so what they typically do is to order a biopsy, most of the times a percutaneous, that use a needle to penetrate it from skin to the organ until reach to the abnormal area and get small piece and do a lot of examination tests, lab tests. And then they can determine whether this is a malignant tumor or it's just a normal tumor. Okay, and also do the treatment. Well, the point is the biopsy. Okay, so you can see this is an example. That is a CT guided biopsy. So because human tissue dynamics is inhale and exhale every second. Okay. And then, due to the inhale, exhale, the contrast will be changed. And sometimes physicians is very hard to find the lesion area. And what they do is, what they typically do is they feel the resistance difference because the tumor typically has a mechanical property difference from the normal tissue. And they feel they cannot easily push the punching the needle inside, keep going on. So they feel, okay, this is the right area to get the biopsy sample. So however, such method may cause, maybe not even touch the tumor, over penetrated or just a slide by the tumor. All of these cases may cause the diagnosis accuracy decrease. So especially when the lesion size is smaller than 1 centimeter. And also they need to do rebiopsy or delay treatment. Okay. So what we did, is we develop such a soft electronics and integrated on the commercially available standard biopsy needle, and we can solve such problem. And the principle is very simple. So we use the piezoelectric nanomembrane as both a sensor and actuator. When the actuator is working, it can shrink and expand, and then the soft needle may be bend in the tissue. And the stiffness difference of the tissue may cause the feedback difference, and then we can feel the feedback difference. And from the sensing signal difference, we know the stiffness of the tissue. And here's a video show we do the artificial tissue with a different modulus layer by layer, and we slowly penetrate it from top to bottom. And you can see the number changes the time, the real time dynamic. So we can use this number as the very accurate factor to determine whether we group a tumor area. Okay. And of course, we did an animal experiment and collaborate with real clinics, physicians. And use the liver tumor mode. So in like a liver transplantation patients, and from different points, and we measure our technology is very accurate, can distinguish the difference from tumor tissue and normal tissue. Okay. So based on this idea, we think whether we can use the skin integrated device to solve some skin disease or skin tumors. And because one thing we cannot ignore is the skin disease ranks the number 4, the leading cause of non-fatal disease burden worldwide. Okay, so when you want to do the characterization of these diseases, so you go to the clinics, so they use the indentation, all these skin suction torsion, or the colorimeter or MRE, need very professional instruments. And so only very few clinics can do this convenience walk-in measurement. So thin soft electronics for this type of non-invasive skin mechanical property measurement is very important. So why we say that? Let's use the melanoma, for example. So this is very well known. So the skin cancer with different stage, which keep penetrated into the deep tissue. We need to measure the skin mechanics from different layers of the tissue, not only the surface of the skin, but also the in-depth of the tissue. So we published this work, and we suggest a very simple method with one sensor and one actuator for these skin mechanics measurement. And the principle is very simple. Mechanical actuator provide force, and then the skin deformation will cause the sensing signal difference. And measure the sensing signal difference, and we know the stiffness difference. And you can find the actuator is very similar to the previous actuator work. So that's true. So we use a similar design. So electromagnetic based actuator, so also based on Lorentz force, because it can provide a very large force. And the whole device is very small, can be just put on the tips of the finger. And so due to the device is very small, so the nature feel this can solve a lot of problems in the such as Africa region. So all the Australia who suffer from the skin diseases, skin cancer, and need on-patient measurements for every single minute. And they made an interview for me and also published in this Spotlight. And because our sensors really work very well, can not only detect these skin cancer, but also some very typical skin diseases just by measure the mechanical difference from the normal tissue, normal skin, and the lesion area. Okay. So now let's go back to the electronic skin, the human-machine interface area. So one thing is very important is a haptic interface. The other thing is the sensor. So sensors, we're also working on a lot of work, such as we use the novel processing route to screen print these rubber type of piezoelectric sensors on top of the soft surface, which can not only be very flexible, but also exhibit very high sensitivity and also very stable performance, no matter your work is used for how long. So it's still working very linear. So with this stable output. So one of the importance of this work is that we can use the one-step screen printing to make high-resolution sensing units on the soft area. And you can see that we can even distinguish the screen distribution of the fingertips and from this device. And so based on this sensor, we can also control the robotic arms and do a lot of things. And based on the wireless skin electronics method, we can control the device like this, okay? So another area we keep working on is to explore more self-powered sensor. So one thing is the triple electric nano generator. People know that this is a very advanced so energy harvesting technology. So however, we always think about so whether we can combine this one with our well-known epidermal electronics together to realize such wearable and skin integrated so triple electric nano generator, not only for energy harvesting but also for sensing. Okay, and we did some work from fundamental study to investigate the coverage area of the skin electrodes on the performance of the TNG in a very thin, soft format. And we designed such a device with considerable stretchability that can maintain good output even under 30% stretching. Okay. So definitely shows potential for sensing or tactile information. Another thing is we think about not only the in-plane stretching, but also out-of-plane is very important, because sometimes we may face such situation. Out-of-plane is very hard suppressing. So we use this trampoline type of based sensor device combined with a microstructure and the mechanics design, and to make such a system so very stable in the performance output to different force. Okay. And which can maintain good performance even under extreme stretching situation. So of course, this device is very easy to fabricate, and we can make such skin electronics patches on top of it. And for this pattern recognition. So another thing is for this one, it's a really combination of the triple electric nano generator with epidermal electronics. And we suggest that this tattoo type also triple electric nano generator. So you can see which can be just like a sticker we play when we are childhood and on the skin. And so which can provide considerable electrical outputs with over hundreds of volts and several milliamperes outputs. And when it's stretched, can maintain very good performance. And we design very Chinese styled device with 12 type of animals, and which can work very well. And it's not only can be used for energy harvesting and collect the electrical signal from daily motion, but also can work as the control panel for the sensing control and to manipulate the robots, so telecar. Okay. So here's the next topic we would like briefly talk about. That's what we're working on. So the past 1 or 2 years. So that's a SWIDE activated battery. Okay. So we know. So now people working on the environmental friendly like a zinc, a water-based battery. But people may overlook the SWIDE. So because we can not only use the SWIDE to activate the bio energy, but also convert the bio energy into electricity. And we use the SWIDE as an activation agent to activate such a primary battery, and use the system level design to make such a device very thin, soft, and stretchable. And you can see that. So this is the first generation of our SWIDE activated battery. And so by changing these components inside of this SWIDE battery, so from the electrode, the thickness, and also the distance, and also the materials volume, and we can realize the performance difference. And in this device, so we can use some artificial SWIDE to activate such a battery. You can see that when the amount is around 0.4 or 0.5 mil per centimeter square, is working, so it's good enough to power the battery. And since this battery is not small, it's stretchable, it's not small, to be honest. So the power density of this one, I think, is not bad. Okay, it can power over 100 LEDs, and you can see that later. Okay, it can power 100 LEDs in a short time. So now, after dropping some artificial SWIDE, it's already good enough. and you use the ohm meter to measure the voltage. You can see that, so it's already has voltage. And when you connect with the LED pad, and so the LED will be lightened immediately. Okay, you can see that. So one of the applications is we can integrate this white battery with some LED, and when people are doing night running, it can improve the safety issue. You can see that when so it can last for 5 hours. It's good enough for night running. So here, so we use this battery to also can activate it. So state-of-art sweat sensors. These are our self-developed sweat sensor, and we can combine them together and use our self-developed app to monitor these sodium pH and so these glucose level. That's in real time. You can see that. Okay. And this is our second generation of the sweat activated battery. Since the previous one, I think it's still too big. So we just shrink the size, use different materials, the nickel and graphene foam-based electrode, and with these magnesium as the electrode, and to power the battery. So we make all the device in a bandage shape, which is good enough to power the state-of-art sensors. Okay, and here is how the device is working. You can see. For this bandage type of sensor, it's very fast, and when you use the artificial sweat on it, it can immediately light the LED. And this one is very flexible. No matter you bend and twist it, so the performance is still very stable around 1.4. Okay. And this is to show how it works. And we integrate these accelerometer and also the pulse rate meter and temperature sensor, and so oxygen, blood oxygen level. In such sensor, and it can be real-time monitored on your cell phone, because it's not only power these sensors, but also the Bluetooth module, all by the sweat activated battery, working up to several hours. Okay, and this is another work. So we keep shrinking the size and the thickness. Here, so we tune the device implant electrode, making the working area in the middle. Not only is the sandwich, it's an implant. Okay, and the device can be even thinner, integrated with these wearable bands. Okay, and so another thing is we consider whether we can keep improving the performance, and we think about it, we use some things as beautiful things in nature. So like how we so rapidly collect sweat. We notice such as the grass leaf and these laser skin, so it's very hydrophobic. So if we can create such structure in the sweat activated battery in a microfluidic format, it can collect the sweat very fast. So we used this idea to make such a microfluidic channel. And you can see that when there's artificial sweat on it, just disperse very fast. Then it can improve the performance significantly. You know, the first generation, the power density is around 10. But here you can see that we improve the performance up to 100. That is the record high performance of sweat activated battery, and which is good enough to power the state-of-art sensors and powered by the Bluetooth, and which is good enough. Okay, and so due to the time limitation, I think I have no time. So there's several materials work we haven't talk about, such as the organic, so electrochemical transistor. We just publicly collaborated with Professor Tobin Marks and Professor Antonio from Northwestern University and published in Nature Materials, which can be used in skin integrated electronics. So at last, so as a summary, so from materials and devices point, we can make sensors and integration electronics, and for the system level application. And in the future, we believe the soft electronics has many areas can be implanted in. Okay, and here is the acknowledgement. So of course, so the collaborators, so Professor John Rogers, so and Professor Tobin Marks, Professor Antonios, and Professor Yonggang Huang. So they still keep giving me a lot of support after even I graduate and leave their group. Okay, we still have collaboration. and Professor Juncheng Yu from USDC, and also several professors from CDU, and also Professor Xie Zhaoqi and Song Enming from Dalian Tech and Fudan University, and of course, so my students, the research staff. And without them, so we cannot share with you these great works. At last, thank you. So now it's open for question.